Can you try now? So as I was saying, I will chair the session. Linda will be co-chairing, and she'll remind you in a little bit that you can ask questions in an anonymous way if you want to by filling out some form on our website. You can also ask questions to Jan either in the middle of the talk, if that is fine for Jan, or in the end. This depends a little bit on what Jan wants to do. I don't know what you would prefer, Jan.
Please go ahead. If you have questions, you can interrupt me and.
Okay. Perfect. So we can have a dynamic seminar with some nice conversations. Then let me introduce Jan. Linda, please, you could start recording if you haven't already. So Jan did his master's in Munich at the LMU in the theoretical and mathematical physics program, and recently finished his PhD with Daniela Caramuro in Leipzig on the topic of energy inequalities in integrable quantum field theories. Jan has recently started a postdoc in Vienna at the IQOQI, I believe working on, measurement in algebraic quantum field theory. If I'm not mistaken, surely you can correct me afterwards if necessary, Jan. And yes, we are very much looking forward to this talk on quantum energy inequalities in integrable models. Please go ahead, the stage is yours. Yeah, we're looking forward.
Okay, thank you all for being here. Thank you for the nice introduction and for having me here. I'm really pleased that I can give a talk here. I'm afraid my topic is not completely aligning with quantum gravity. It has a strong relation with semiclassical gravity, and at the very end, I may speculate on some connections with quantum gravity, but with full quantum gravity. But yeah, forgive me if there's not the strongest connection with it. The topic is mainly based on my PhD work, which I conducted at Leipzig, as Jose said, and it's based on two publications whose preprint numbers I put below. The talk has two ingredients, energy inequalities and integrable models. And to start with, I will explain these two ingredients. And their connection can be mainly given by a central observable, that's the stress energy tensor, quantifying energy fluxes and energy densities in the quantum field theory model. Also in classical field theory, you can have it. Now, given these introductory part of the talk, I can then explain my two main results that I will present. Namely one particle and two particle QEIs, and then I will explain later what exactly this means. But first, let me give you a small teaser on energy inequalities or negative energies. So to start with, here is an image of a wormhole, and you can cook up many other exotic space-time geometries like warp drives or closed time-like curves. And what they all have in common is that they require some negative energy to be sourced in general relativity and also semiclassical gravity. So this is one place where negative energies are somehow needed, or you can take the other perspective where if you don't want to allow such space-time geometries to be reasonable, where you need further restrictions in your model to exclude them. This role will be played by the energy inequalities. A physical model where negative energies are present, which is well tested, is the so-called Casimir effect. So here I put a drawing of that I did myself, as is easily visible. But so in black, you have two conducting plates. And if you bring them close together, what you will find is that the energy density in between will be less than outside. In other words, it will be negative inside compared to the outside. And this will result in an attractive force, which holds the plates together and is known as the Casimir force. So this is one particular example where negative energies are also known as, in terms of a well-tested phenomenon. And the thing is now that in quantum field theory, there are general arguments. Oh, okay, here's the pulling together of the plates. And the thing is now that there are general arguments already from the 60s that negative energies in quantum field theory should be abundant. I will not go into detail about these arguments and so on, but this is one key point here, that one has to deal with them in some way. Now, I already talked about that there should be maybe some constraints on how much negative energy you can have in such a model. And the first thing to look at is maybe at point-like quantities. So at the point-wise energy density, but here's the fact that it can become arbitrarily negative. That there are no direct constraints or like you could see as a consequence of the uncertainty relation, at least heuristically. So if you think of energy and momentum, if you like the uncertainty in energy and momentum becomes infinite if you scale down to arbitrarily small times and spaced distances. So in this regard, you don't expect that the point-wise quantities have any strong constraints. Now, there should be some, but there is the fact that on large scales, like if you go to macroscopic scales, there are some arguments that you need bounds on the negative energies because your model would not be stable. So one thing you can think about, like if we want to talk about some Gedanken experiments, you can take some source of radiation, which has a negative energy flux, and point it at some other system. Now, with this negative energy flux, you can reduce the energy, and you can also hook up a setup where you cool down this system. And if this radiation is pure, it will not convey any entropy change, but the system cools down. So in the end, you can create a violation of the second law of thermodynamics. And while in macroscopic systems, this is not a problem, in macroscopic systems, that would be a problem. We don't observe macroscopic violations of the thermodynamics. So in this regard, at some scale, there should be constraints on how much negative energies or fluxes there are present in the model. In this sense, we need some stability constraints. And you can make further thoughts of what form they can take and so on. And for instance, you can think about, okay, this negative energy, it should not become arbitrarily big. Now, note that I talk about negative energies now, not densities. So what I mean is basically if I integrate over some region in space-time, the energy density, like I average the energy density over some region of space-time, then I get a negative energy. And I would expect that these chunks of negative energy cannot become arbitrarily large. And also I would expect that they cannot endure arbitrarily long times. So after some time, they should dissolve with positive energy bits in the environment. So putting this all into one unifying mathematical framework, this is basically what is called a quantum energy inequality. And like one formulation of it would be, I consider the stress energy measured by some observer, which follows a trajectory gamma and averages its observations along this curve with a test function that is positive, noted here as g squared. And depending on how this curve, if this curve, for instance, is inertial or not, this observed energy flux or density will change. For the rest of this talk, I will focus on inertial curves that are time-like. So I will basically look at the T00 component of the stress tensor. You can just as well also look over as the stress energy smeared over space-time region, but like for later, I will just focus on these trajectory observer dependent stress tensor, average stress tensors. Now, what is a QEI? A QEI is now if you say that this energy density, this averaged energy density in some class of vector states. Do you see my pointer, by the way? Yeah, okay. So if you evaluate the stress energy, the average stress energy in some vector states, then it should be bounded from below by some constant that depends only on the weight function and the curve, but not on the states themselves. And this should hold within a sufficiently large class of reasonable states. And this generalizes classical energy conditions that are known from general relativity, where you expect that this average stress energy is positive or non-negative, to be precise. Now, okay, what is known about these QEIs? They are already around since the late 70s or beginning 80s, but there's a lot that has been done. And for instance, okay, there are direct connections with other stability criterions through QFT. Maybe let me go once more back. So by choice of the profile of this averaging function or the scale at which this averaging function operates, you basically choose also the scale at which your energy constraints should hold. And in this sense, these QIs interpolate between microscopic and macroscopic constraints. And this is precisely what this sentence is alluding to. Now, this is established for free QFT, like without interaction, and also like in semiclassical gravity, where you couple the average stress tensor with the geometry. You can derive some nice properties, namely that these QIs can have similar consequences as classical energy conditions. So I'm not sure how well you are familiar with these results, but for instance, there are singularity theorems which tell you that if you have some positivity of energy, basically a sufficiently accumulated mass in the system, then your geometry needs to collapse to form a singularity. And this classical result can be generalized to semiclassical gravity by using these QIs. And this is one of the main connections now with semiclassical gravity. You can also exclude some exotic spacetimes, as I mentioned in the beginning, like wormholes. So there are a lot of nice results that in this direction. And you can also establish that these QIs hold in many kinds of free QFTs in both flat and curved spacetimes. So not only they have nice consequences, but they actually hold in many models. But what is not so much known, or where's little known about, is what happens if you put interactions. There's some weaker bounds in generic settings, but for those it's not known if they have similar consequences as I mentioned at the beginning. And there are some limited results in a few examples with self-interaction, namely basically these two. And I will build up on a part of that. So as you see there, my supervisor is listed there. So the main result I will build up on is this here, that for integrable models, you can also like have partial results at the one particle level that tell you that QIs hold. But yeah, one of my main results is that I generalized this in particle number and types of particles. Okay, so this is so far the side of QEIs. So in this sense, it would be a good moment to stop maybe for questions if you need some clarifications on this part of the topic. So are there any questions on QEIs? Go back here.
seems that not. You can go ahead, Jan.
Mm-hmm. Okay, so my second part of the topic is integrability in QFT or integrable models. Now, the thing is, if you want to talk about interaction in QFT, there are not so many options aside from the perturbative standard formulations like Lagrangian QFT. Problem with perturbative formulations is that there is no good control on energy inequalities possible, because you don't have a convergent series in the coupling constant, and then you cannot really prove meaningful bounds there. So you would need some non-perturbative formulation of interaction, and there are not many models which are rigorously constructed in this fashion. But one rich class of models are these integrable models, which are models in 1+1 dimensions, so one time and one space dimensions. And I explored basically what is happening with energy inequalities in this setting. Okay. So first, what is integrability? Well, you can connect integrability, like in general, integrability of a dynamical system means there's you have a complete set of independent conserved charges, and since QFT is an infinite dimensional system, means you have an infinite set of independent conserved charges. And from those, you can basically integrate the dynamics. So if you fix these conserved charges, you already know in which orbit in phase space you are. And like QFT is usually formulated not in some phase space language, but rather in terms of scattering theory. And you can also derive some constraints in scattering theory. And in particular, the scattering theory will be March constraints. So, for instance, you have no particle creation, and the scattered particle momenta will stay the same. So that is a huge restriction of these scattering models. In a sense, it's a QFT model that is close to a billiard ball model, because like in usual QFT, you would have particle production, but here you only have changes of colors, basically, also of particle types and charges upon scattering. And moreover, you like the scattering factorizes into elementary building blocks of 2-to-2 particle collisions, like depicted on the right. So you just it's like every n-to-n collision you can write down as a succession of 2-to-2 collisions. This is known as matrix factorization. And last but not least, you can show that only in 2 dimensions you can have non-trivial S matrix. So in all high dimensions you get just the 3 models. While this seems a bit like, okay, this is highly restricted, there are plenty of models that you can formulate, and some of them also have relevance as toy models to, for instance, the nonlinear-sigma models are sometimes used to approximate some effects of QCD, and also string theory, these nonlinear-sigma models appear, and there are many other connections with more physically reasonable models in QFT. Okay, and let me also not mention how they are how you can construct them rigorously. And this is usually termed the construction with the inverse scattering approach. Namely, what you can do is you can fix the asymptotic data of your model, so the particle spectrum and the S matrix. And what usually is not successful in QFT is here successful. Namely, you can reconstruct the local field content from just the asymptotic data. And this is known as the form factor program. I will not mention any details, but it's a very nice result that, like, by just fixing basically some kind of boundary data, you can reconstruct what is locally happening. And it's a consequence of clear consequence of integrability. Okay, this should be it for the general introduction to integrable models. And I would now move on to discuss the stress tensor in such models. Namely, if you recall how an energy inequality can look like, what is centrally appearing is the stress tensor. So we should discuss what properties it has and so on. The problem now is that while in usual QFTs, where you have a Lagrangian or an action, you have a direct mechanism or direct formula to compute the stress tensor. This is not directly available if you use this inverse scattering approach. So what I will do is I will take an axiomatic viewpoint on the stress tensor and say, okay, what properties does a stress tensor usually have? And then see if this class of possible observables is maybe sufficient to fix me what is the stress tensor. Okay, and the main property, like, okay, so I'm now on Minkowski spacetime. The main property here is that if you have a Noetherian point of view on the stress tensor, then you would say that the stress tensor integrated along the space-like hyperplane gives you the charge, so in this case, the total energy momentum operator, and that the stress tensor is conserved, meaning it fulfills the continuity equation, or in other words, it's divergence-free. Moreover, you would say that the stress tensor is a two-tensor under Poincare transformation or under Lorentz transformations and is translationally covariant and is symmetric. And these are the main properties. Now there are some more that are needed to really fix or pin it down. For instance, you would usually require that the stress tensor is chargeless under global symmetries. CPT is always a symmetry of a QFT, but there might be more. And you impose some regularity. So the high energy behavior should not be arbitrary and so on. With all this, you can then look in a concrete model and see if you find a nice class of observables that satisfies these properties and ask, is there a stress tensor? And if there is it unique? Okay, back to our aim, the energy inequalities.
Sorry, may I just ask a quick question on the previous slide?
Yeah.
So do you expect generally that the energy momentum tensor can be integrated out to give something like a generator of translations, even if the translations do not induce isometries of the metric?
No, in this case, I would not expect it. So this is here like a Minkowski specific.
Right. That's so. In the same question for the Poincare covariance that you are suggesting. So this is only for metrics which are somehow invariant under Poincare transformations.
Yes. So the thing is, since I restricted 2 dimensions and every metric is conformally flat, there is some, like, one could now introduce artificially curvature, and maybe it's also interesting, but like, I mean, basically, interaction is already complicated enough that I focus on Minkowski with my research.
Fair enough. Thank you.
Yeah. For curved spacetimes, you would then have come up with different properties. Yeah. Okay. So, okay, back to our original aim. We want to obtain some energy inequalities. I put now the 0,0 component, so we will really fix an inertial time-like curve. So and ask then, okay, what form can this expectation value have? And the thing is, since in integrable models you have particle number conservation, you can restrict meaning in a meaningful way to states which have a certain number of particles, and the stress tensor will not, you can restrict to definite numbers of particles, and the simplest thing you can start with is one particle states. Okay, so what form do they take? Okay, so that's what is meant if I talk about one particle QIs. I restrict to states that have one particle, where the number operator is 1. Let me mention that while this seems a bit trivial, because why should there be interaction already? The thing is that in these integrable models, the interaction is ingrained in the observables already. So in this sense, the interaction already plays a role in the one particle expectation values. Okay, so for simplicity, and I will restrict to a simple setup. I need here parity covariance, and I will restrict to single mass sector. And I can then classify the general form of the stress tensor. And you have some universal ingredients in this general form. First of all, covariance fixes me to have these terms here. First, we have a canonical one-particle expression of the free stress tensor of a scalar field in this case. And a translational factor. And this is completely fixed by covariance. Let me note in 2 dimensions, or 1 + 1 dimensions, the mass shell is parameterized conventionally by rapidities, theta and eta. So basically they parameterize momenta in 1 + 1 dimensional space. And the rest is the states labeled with particle type and charge labels, alpha, some discrete index, and an integral kernel that depends just on the difference of the rapidities. And this integral kernel is the only thing which depends on the interaction. So it seems reasonable to ask, do energy inequalities hold dependence with quantifying the dependence on this F? Okay, and what can you prove? So it's a bit technical here, but let me just say that if you have an asymptotic bound on this growth of the F, then you can show that QEI holds. And if you have an almost exact reverse, so it's not quite exact, but if you have that the growth is larger than this, then you can show that no QI can hold. So there's an almost, yeah?
Yeah, and there's a quick question in the chat whether the H1 denotes a one-particle Hilbert space.
That's correct, yes.
No. Thank you.
Yeah, so in a sense, and I should note that these are now results that of mine. Okay, okay, so there's this almost classification. So together with my supervisors, and this almost classification tells you the only thing that one particle QIs depends on is this asymptotic growth of this F. There's a small intermediate setting where we don't have a conclusive result, but it's an almost classification. Now, the thing is, the F is not immediately connected to the input of the construction, the scattering matrix, but you can do this, but then you have to talk a bit more about the specifics of integrable models, which I would refrain from doing now in this talk. But the important thing is you can say if a QI holds or not, and what is really nice about it, I don't have a slide for it, but is that you can now say you can add to your axiomatic perspective of the stress tensor the one-particle QIs as a physical requirement that you would expect from a physically reasonable, stable model. So if you recall what I said in the beginning for these energy inequalities, that they are stability properties of your model, you can say, okay, the validity of such energy inequalities should be maybe part of definition of the energy density or the stress tensor, and could be a meaningful property here. And the nice thing is that in some of the models, you can show that actually adding this property, you can completely fix a unique stress tensor. In this sense, you regain what you would like to have, namely, you can uniquely say what the stress tensor in your model is.
Yeah, another request for clarification in the chat for the notation curly D of RK.
Yes, okay. It's the compactly supported functions on the real line, smooth functions on the real line with values in some discrete Hilbert space K. And K basically should stand for the particle types and colors. So important part of this result was also that I generalized to models with arbitrary particle types and charges. This is basically why but you can also think of just scalar models where all these discrete indices go away. Yeah. So maybe just to clarify what I mean here. So this no-go result is, okay, if you have this asymptotic growth, then you find a sequence of states where the energy density in this sequence diverges, so no QI can hold. Okay, and this concludes the one particle QI part of the talk. So maybe also if there are further questions, it's a good time to stop again. Okay, if there are no further questions, then let me move on. So I looked at one particle QIs, but it would be interesting what happens at higher particles. Like there are plenty of different states that are more complicated and but still physically reasonable. You would like to have actually results for any particle number, but it becomes very complicated, like to treat this analytically. And I was not successful in doing this, but I proved, or I gained some numerical insights that I would like to present to you. This is also important because, like, for instance, these bounds, they are not quantitatively. So you don't know, you can just say if QI holds or not. So you cannot really quantify what are these lower bounds, this constant CG gamma that I put before. And you cannot really say, like, how negative does the energy get? So this is now the last section that I would like to present, namely sharp 1 and 2 particle QIs. So the 1 particle QIs are still included because they are now sharp, at least approximatively, because we do numerics. And for simplicity, I will focus on a represented or a prototypical model, the sinh-Gordon model. Like, it's the simplest type of integrable model you can have, where the S matrix is dependent on the energies or momenta of the scattering particles. So theta is here the rapidity difference of the incoming particles, and this is a 2 to 2 particle scattering function. And if you recall my slide from the integrable models, this is sufficient to completely fix the scattering theory of the model, because this S matrix is factorizing. Now, like, it has one physical parameter, the coupling strength B, and it can range from 0 to 2. And there's a symmetry B to 2 minus B. So in the end, only you could restrict to B running from 0 to 1. And it's a model like of one scalar particle, and like maybe more or better known is the sinh-Gordon model, where you have an oscillating, a sign potential, and the sinh-Gordon model is kind of an analytic, like a Wick rotated model, where you have a sinh as a potential instead. Okay, we fixed this model and hope that. We fixed this model, and now we look at 1 particles and 2 particles. Now, in the 1 particle setup, we had this F appearing. Now, this is denoted as F2, and it so the notation is because you have a 1 particle state on the one side, on the one on the other side. So the usual label is then the sum of the particle number, so it will be always 2 times the number of particles. So F4 stands then for the 2 particle contributions. They have some complicated form, but like these P factors are fixed by covariance mainly, with some freedom in your like the properties of the stress tensor leave some freedom here, but we take a canonical choice. And there's a interaction or a uniquely defined factor that quantifies the interaction, that's called minimal solution. We don't need to go into any details about these, but let me note that the 2 particle case is much more complicated because suddenly you have 4 arguments and you have some kinematical singularities here. So if you want to treat this numerically, what you can do, you can, okay, first you can choose a fast numerical representation for f min, since it's a bit complicated to write them down. And the second thing is you can discretize in rapidity space. And what you need then is a regularization of the singular parts of the form factors, which this is the name of these factors. One way is to choose an I epsilon prescription where you take a finite epsilon here. But this is very slow. And what I did is I computed analytically what happens if you average over such a kernel in a certain cell, and then you can sum up this discretized contributions. Okay, okay, and as I mentioned, I discretized the rapidities on a lattice. I have some UV cutoff, mainly so big R, which restricts the size of the rapidities, and we have n points per variable, meaning that the stress tensor will be an operator in a discretized space, so basically a matrix of n to the k times n to the k variables, where k is the particle level. So you see that the complexity of this problem scales exponentially in k. So you don't expect this to work in any high particle levels, but for 2 particle levels, it's still possible. And the reason why this is the case is that you need only the lowest eigenvalues of the stress tensor. So you do a spectral analysis, you only compute the lowest eigenvalue, and this is your lower bound for the spectrum of the stress tensor, and thus for the energy inequality. And okay, what do you get? I mean, this was now the technical introduction. And one last thing. Okay, when do you accept the result of this analysis? Well, when it converges in the artificial parameters, namely the number of discretization points and the cutoff. So if your result does not depend on them anymore, has some convergence properties, then you would accept this result as meaningful outcomes. Okay. Then what are the results? First of all, okay, last reminder of how these energy inequalities look like. K is the particle level. And here you see the dependence on the interaction quantified by the coupling constant B. What you see is in blue is always the 2-particle level, and in red is the 1-particle level. The 1-particle level was previously known, and this has very strong convergence, so there's no convergence indicated here. And what you see is stronger interaction means you can get more negative energies. This is not really surprising, but it's already a nice outcome. Like basically interaction can create some negativity or some negative energies. What you also see is that at the 2-particle level, you can have more negative energies with some caveats on the boundaries of this diagram where the convergence is not so good. Okay, what more can you do? Well, you can also ask, how does this negative energies depend on the averaging? In particular, you can choose a specific averaging function g squared, for instance, a Gauss function or a Lorentz function. And this has a natural scale, like the Gauss function has a width of the curve, which gives you some natural averaging scale. And you can ask, how does the negative energies, how do they depend on the averaging scale? And what you find is that they have some universal behavior for very small averaging scales, so in the microscopic regimes. This is expected that the stress tensor has some scaling properties. And what you also see is that in the in large averaging scales, recall, by the way, that these are time scales, but in principle, you would also expect this for space scales. Like for very long times, what you recover is basically positivity. So on the left-hand side, you have the also a logarithmic scale. And these edges are just numerical artifacts, so maybe you should end the plot here to be reliable. But what you see is definitely you tend to positivity in macroscopic scales. So in the end, for instance, you don't expect any macroscopic violations of the second law of thermodynamics, for instance, if you would like. Okay. Last but not least, what you can also do is you can look at non-minimal expressions of the stress tensors. So I mentioned that we can take a canonical choice. We can also ask what, like after fixing the general properties of the stress tensor, are there other candidates? And what you find is that in these simplified models, the freedom of choice to add to a canonical stress tensor different additional terms is basically to add box operators of this canonical expression. And for high powers of the box operators, you can directly show that no energy inequalities holds by this by this analytic one particle results. But for one box operator is actually allowed. And now you can parameterize the freedom that you still have by a single parameter, nu, where nu equals 0 would correspond to the canonical choice. And you can then dot the negative energies against nu. And you see that in the one particle case, you have some corridor in which energy inequalities can be valid. And at the two particle level, you also have it, but it's much more narrow. And the expectation would be that at higher particle numbers, this corridor gets smaller and smaller. And my speculation would be that if you go to arbitrary high particle levels, you would have a single remaining candidate, which is the canonical stress tensor. And thereby you could then infer that the validity of QIs basically imposes the unique choice of stress tensor, namely a canonical one, at least in models where a canonical expression is available. So this is how I interpret these results and how they give rise to some nice expectations about what could happen or how these energy inequalities could be used also in interacting models. With this, I can conclude and summarize what I've talked about. So first of all, I mentioned these one particle QIs. They hold in a large class of models with different particle types. I can also include bound states and all kinds of discrete degrees of freedom. And there's some general classification on these energy inequalities. And the second, maybe even more important result is that QEIs can be imposed to select physically reasonable stress tensors in situations where unambiguous definitions don't apply. So, and this should be maybe one message that I could send or could connect speculatively to quantum gravity. But I should say this is not based on anything which I've done in more detail. But the one setup which is closest to QFT for quantum gravity, like asymptotic safety, I think you had this in the seminar a number of times, so I hope that you're familiar somehow with asymptotic safety. I would expect that maybe in asymptotic safety, so there it's important so there you have non-minimal terms in the curvature tensors. And these non-minimal terms are mainly restricted by the assumption of asymptotic safety to a finite number of parameters. Now, so it's very important there to restrict the number of free parameters that are fixed by experiments to gain predictability. And I would hope that maybe at some point, but this is maybe too early, one can have similar stability conditions as energy inequalities to also have a nice way to restrict this set of parameters to maybe even increase predictability or have some different perspective on these questions. Okay, that's one speculation I wanted to mention, maybe just to honor this seminar series. Lastly, let me note that it would be nice to have analytic results also for higher particle numbers. And with this, I should conclude and thank you for your attention.
Thank you very much, Jan.